Good afternoon, this is Mr. Schweitzer, and we're going to walk through a couple of worksheets here on equilibrium concentration determination. Alright, so here we have a reaction where it's giving us an equation. I'm going to rewrite the equation: N2 plus 3H2 to 2NH3. It's giving me a K value, and it's a Kp value, so we'll be dealing with pressures in this as opposed to moles per liter, partial pressures. We have 1.45 E, and they have fifth at a temperature. One thing about the temperature is this thing is required, not necessarily to the problem, but just that K is dependent on this temperature, and this temperature depends on that K. So if the temperature changes, so does the K value, and you should be somewhat aware of that. An equilibrium mixture of all three gases, so in an equilibrium mixture, that's important. The partial pressure of H2 is 0.92, N2 is 0.32. What will be the partial pressure of the NH3? So let's just start an ice table and just start filling in what they give me. My Kp is equal to, no, I have gas, this should be a gas, and then they're all included, so it's N, the NH3 squared, NH3, the H2 cubed, the N2 single. They're only giving me equilibrium concentration, so in this case 1.45 equals the NH3, which is going to be, we don't know that one, X, unknown, squared. And then we have this guy, someone put this guy, we don't know this piece. This one right here is 0.928, and this guy is 0.432. Now again, in order to maintain a balance of 1.45 e to the negative fifth, then I would have to have a certain ratio between products and reactants. And since we know two of them already, the third one is just a matter of process of elimination. 0.432 and 0.928 cubed. Solve for x. At this point, literally just multiply out the bottom to multiply it up, and then cube square root to find x value. So 1.45 e to the negative fifth times 0.432 times 0.928 squared. This gives me 5.39 e to the negative sixth. I'll then square root that value to eliminate the k value, the square on the other side, and I get x equals 0.0232, and there's two zeros on there. 0.00232. That's in moles per liter, and that's the concentration of X that will balance at this K. That's the answer to the problem. Alright, a flask, a 1 liter flask, is filled with 1 mole of H2, 2 moles of I2, and calculate the value equilibrium constant Kc for the reaction above. So calculate the value equilibrium. The value of the constant Kc is this. What are the concentrations of the reactants and products at equilibrium? Okay, so let's rewrite the problem. H2 plus I2 yields Hi and there's square. Initial stoichiometric ratio end. I have 1 mole per liter. This, notice 1 mole in 1 liter is 1 mole per liter. Note they're holding 4 sig figs here. So we want to hold probably 4, although the K value only has 3, so we would end up having 3 in our final calculation. So you go with the smallest. 1 molar for, actually this guy is going to be 2 molar, and there's none of this. So we will be shifting towards products to attain our equilibrium value, which is pretty close to the middle of the pack between reactants and products. Minus x minus 2x, oh, no, that's just going to be minus x, and plus 2x follows 1, 1, 2. So at this point, if they were to give us one of these equilibrium values, I could easily find the other ones because I could then find x. But they don't. Instead, they give me the k value. So the k value for Kc is equal to the concentration of Hi squared, concentration of the H2, concentration of the I2. And in this case, I'm going to plug the values in. I'm going to get rid of my squares here so you can see a little better. 1 minus x, 2 minus x, and is 2x. These values would represent the concentrations at equilibrium. So it's going to be 50.5 equals 2x squared over 1 minus x, and then it would be 2 minus x. At this point, we've used our shortcut rule in the past to eliminate these x values and to try to make the problem simpler. But in this case, I'm actually product favored, and those x's are fairly substantial in size. So eliminating them would not work. This k value needs to be much smaller. So I'm going to take a moment, and the AP does not require this calculation, but let's just show the algebra here for a quick moment. Let's go grab a new page here. So I have 50.5 equals 2x squared over 1 minus x times 2 minus x. I do believe that is correct, and it's right here. So let's go ahead and show this. First of all, I'd FOIL this thing. 1 times 2 is 2. Negative x times 2 is minus 2x. Negative x, so I just did this guy times that guy. Then let's just keep it consistent here so I don't screw myself up. And then let's go this times that would be a negative x. This guy times that guy would be a negative 2x. And then a positive x squared. That's the bottom. And then the top is this 2x. So I'm going to take this 2x squared item, multiply it up across the 50.5. So I got 50.5 times 2 minus x minus 2x minus x squared equals 2x squared. Distribute. It's going to give me 101 minus, I'm going to combine these two guys to being negative 3x. So 3 times 50.5 is 151.5x, and that would be negative. And then minus 50.5 x squared equals 2x squared. At this point, I would subtract off the minus 2x squared. 50.5. Pretty simple calculation, just subtracting 2 essentially. Gives me 101 minus 151.5x minus 50 point, not 50 anymore, it's 48.5x squared equals 0. Now this is just a quad form. You could then take this thing and run it through the quad form, which I will do. This is my A component, this is my B component, this is my C component. Quad form, punching A as being negative 48.5, negative 151.5, and 101. And I have, make sure I got everything right. Alright, unless I made a sign error someplace, which is always possible, I have a negative 3.68, and because we get 2 of these guys, equaling a 0.564, and I believe that if that's the case, this is the only one that will work here. So 0.564, let's jump back to the other page. X equals 0.564. Notice that value could then slide into here, here, and here. 0.564 would be 1 minus 0.564, 2 minus 0.564, and then 2 times that. So let's go ahead and just finish this up. I got 1 minus x, 2 minus x, and then 2 times x. So 1 minus 0.564, 2 minus 0.564, and then 2 times 0.564. So 1 minus 0.564 is a 0.436. 2 minus a 0.564 is 1.436. 2 times a 0.564 is 1.128. And these are my concentrations in moles per liter of that problem. Now again, we went through some extra work here in order to use the quadratic formula to see how we might get that, but on an AP exam they do not require you to do the quadratic formula. If it looks like the K is too big and I can't use my shortcut of removing that X value, notice that X value is 0.5. That's almost half of it. In this case, you would look for other ways to simplify, but unusually not needed. Alright, a reverse reaction, as seen here, has been used in the commercial source of hydrogen. We got a value of temperature, and it says the equilibrium concentration of these gases was found at half, so equilibrium concentration, that's relatively important. I have, in this case, we write the equation, CH4 plus H2O, CO plus 3H2. Everything is gases. I have a coefficient here, so my K, I'm using concentrations, and it is going to be the concentration of the CO times concentration of H2 cubed, concentration of CH4, concentration of H2O, and at that point they're giving me equilibrium concentration, so it's CO is 0.30, H2 is 0.800, and the CH4 is 0.40. It's saying if the Kc is 5.67 for this reaction, what's the concentration of this guy? So again, all this goes in here. 5.67 equals the 0.8 goes here, the 0.30 goes here, and the 0.40 goes there. And I am looking to solve for the H2O, which is the other component right here, X. X marks the spot. Alright, at that point, 5.67 times 0.4 equals, okay, 2.26. Divide this thing by 0.3, and then divide by 0.8 cubed. 14.7. In this case, I'd moved this up here, and then I moved this thing over, left my X in the bottom. At that point, having X in the bottom, it's going to be 14.7 equals 1 over X. And I would just simply reciprocal that thing, and I get X equaling 0.067 moles per liter. That's maybe a little bit different way of doing it, but if you're solving for a variable on the bottom, your best bet might just be to move it to the top right away. And that way, you don't got to worry about having it on the bottom. Alright, and next problem. Looks like we got a couple more here. Alright, a few more, maybe too many here. Alright, we got the reaction between CO. Okay, so the reaction 4.6 is the K value. If this number of moles placed whenever it can, at what vessel, what concentrations are reactions held and when it reaches equilibrium. Alright, so we have a bunch of problems like this one, and they all seem very similar, in which case they are. Alright, let's solve this one out here. We got CO plus H2O, CO2 plus H2, so my Kc equals, and this looks like this thing is balanced for you. They usually come balanced. The concentration of H2 This one here is slightly different than the one above it, you might notice. So they start to all look the same after a while. The concentration of H2, concentration of CO2, concentration of CO, concentration of H2O, all ones, all gases. If 0.1 moles of CO, so initial 0.1 moles, and it's in 1 liter container, so we're going to just go right to moles per liter, and 0.1 moles of this. CO2 is not provided, and neither is the H2, 0, 0. As I attempt to attain equilibrium, I will lose x of this, lose x of this, gain x, and now gain x. 0.10 plus x plus 0.10, 0.1 minus x, minus x, x, and x. Plug it in, 4.06 equals 0.1 minus x, x times x over 0.1 minus x and 0.1 minus x. Alright. Now, in this case, we'd be looking for easier ways to mathematically simplify things if you can. In this case, we have two squares here, so we could go x squared over 0.1 minus x squared, and we would therefore cancel out our two squares, equaling 4.06, and then solving for x in this case. Alright. At that point, we'd have 4.06 equaling x over 0.1 x minus x. Multiplying it up, we get, again, more algebra here. We get 4.06 times 0.1 minus x equaling x. Multiply across, and we get, running on their page, 4 times 0.1 is 0.406x minus 4.06x equaling x. And then at that point, we want to get all our x components to one side. I would add this x over, so it's 0.406 equals would be 5.06x. Divide out the 5.06, divide out the 5.06, and x equals a whopping 0.08 moles per liter. That goes right there. Another way to do this is just to FOIL this thing right here, move it up, distribute, move all your x's over, and quadratic. Again, not required on the AP exam. Usually simplification is a way to handle this. The next problem. Let's handle the back side of this page on a second video. This was getting too long. And we'll stop there. Thank you very much.